Okay, so good morning, everybody. Welcome to the conference in Miami. So on behalf of the organizers, I'd like to start by thanking the Simons Foundation and the University of Miami for making this event series possible. So this is the third event in the Hodge Theory special year. And we hope that we'll be able to propose on-site events in Miami next year. That, of course, will be subject to the situation. Okay. So now the topic of the conference this week is O-Minimality and its applications to Hodge theory, plus maybe surrounding subjects. So this is one of the most fascinating recent developments in Hodge theory, where logical methods are applied to obtain new and sometimes previously conjectured results in Hodge theory, analytic geometry, and also arithmetical side of the question. Okay, so it's a great pleasure to have this morning. We'll be having the start of the mini courses by Boris, Zilber, and Bruno Klingler this morning and tomorrow morning. And so our first speaker is Boris Zilber, who will speak on model theory from logic to geometry.
Thank you. Good morning, everyone. I see my task as saying some general things about, to broader mathematical community, to a community of geometers, and maybe a few number theorists, to give a sort of introduction into principles of model theory, and as good as I can do this to explain why logic, once being a formal logic, turned out to be useful to mathematicians. Okay, so I start with history. So here is one of the definitions of what mathematical logic is about. It's very old definition, but in broadest way, it still stands. So it is logic by subject and mathematics by method. Now, there is something quite specific about this statement, because it is this part of mathematics which does have a subject. It is it's almost like physics. So we start by asking questions about nature. Well, although this is not necessarily, it depends on your philosophical view of what is the source of logic. But to some people, logic is as objective as physics. So we do study some sort of side of nature. And the real studies started in early 20th century, and initial questions, of course, were of exactly this logical nature. And so here you see one of the first really powerful theorems that tells you that any meaningful mathematical theory, or let's say a mathematical theory that contains at least arithmetic, we cannot hope to have explicit reasonably explicit system of axioms for this. Well, we can write down some sort of axioms. There are axioms of so-called piano arithmetic axioms, but none of this can be complete. That's the point. And completeness in realm of logic means that your system of axioms is such that it resolves any question, that if you feed into it a mathematical statements, then your system of axioms theoretically can either imply proof of this or imply the proof of negation of this statement. But you see, this answers some maybe deep logical question, but it doesn't help you to prove mathematical theorems. So another, of course, very important run of events at this time was Hilbert's hope that formal logical analysis would result in establishing consistency of mathematics, which was some concern at this point when certain paradoxes of set theory were discovered and other things. So it is old history, but it's still going on. To understand in philosophical terms of what is happening here. And the second Gödel's incompleteness theorem proves that this is not possible. Okay, so but this were pre-model theory times. So model theory came in a bit later, and here I want to emphasize that from the outset, model theory was looking for applications. It was driven by thoughts about applications. It is a kind of idea that if you're good in analyzing logic, in understanding what the proof is, what does it mean that it is impossible in principle to have a proof, can it help to prove mathematical theorems now? And one of the, as you see here on the slide, one of the first papers in model theory, a very important one. In fact, it also contained the proof of, I don't remember now, maybe shortly before this, the same Maltsev proved the compactness theorem. And so this paper, General Method for Obtaining Local Theorems in Group Theory, was actually a kind of breakthrough paper in development of model theory. And so what model theory does, what is different with the previous times, that model theory thinks, sets out formalism. It's a kind of Brubachian formalism of mathematical structure. So you have a structure, and the structure you have a specific language. That's what determines the structure. It is also, it comes with language, and this language is actually well, it has as its vocabulary a list of names of relations or function symbols that you allow to use when discussing this structure. And in fact, when you start with this definitions, such a broad definition, you soon become interested in conditions which make the structure or its formal theory tame. So what does it mean for a structure to be tame? Why some structures are better than others? And here we have so model theory developed. It wasn't from the very beginning, but step by step, the following criteria for tameness. And this are rather criteria at the early stages. So I would say before 1960s, the criteria for tameness So first of all, we already mentioned this, the completeness. So one looks for whether you can write down a list of axioms, at least theoretically, a list of axioms which, of course, are supposed to be true on your structure. And we write this in the form that it is part of the this TH of M is the theory of M. It is a collection of all true statements about M in this language that we have in mind. So part of this, some interesting part of the statements forms a system of axioms, and we ask whether this system of axioms is complete in the sense that I explained. And then the next one is the criteria of categoricity. So categoricity here is the old word which has nothing to do with category theory. The definition of categoricity is that you have your axioms, you have such system of axioms that it is so complete that it determines your structure uniquely up to isomorphism. So it is stronger than completeness. So the theory is so strongly characterizes your structures that it is categorical. It is categorically characterized. By the way, about the same time when logicians discussed this notion, maybe a bit earlier, physicists also discussed the very same notion, but in terms of, well, they called it univocal. So they discussed whether the theory of physics, and Einstein was very seriously involved in this discussion, whether the theory of physics should be univocal. So it defines, it determines unique model, we would say. So categoricity, again, is a stronger assumption than completeness. And in fact, here you see it is important that in this definition, well, I narrowed my definition, my version of this definition, to consider only uncountable size of the structure. Well, you can, without any problem, assume that we are talking about continuum, the size of the universes of our structures to be just continuum, like field of real numbers or field of complex numbers or any usual geometric object. Actually, it doesn't matter whether it is continuum or any other uncountable cardinality, as was proved by, so it was a great theorem that started this business in series by Michael Morley in 1960s. Okay, and then the third assumption, the third condition that we look at when we study a theory of a structure is whether we do have classification of definable subsets. And I'm going to give quite a few examples, but before even I go towards these examples, you see, so what typically is a definable subset of, let's say, you have you have a affine space, say, over the complexes, and what is definable if you only use addition and multiplication. You can write down an equation, just usual polynomial equation, and and by this you define some curve or surface or some such thing, and this is a typical definable subset. But because we are talking about this logical languages that also allow not only write down equations or negate these equations and take conjunction between them, but you can also use quantifiers. You can say, for all x, I should be able to find y such that y squared is equal to x. So this sort of property, so you cannot express it without quantifiers. And so you have much more power of definition, and so you want to classify this. So what are these definable sets? And quantify elimination theorem is one way of saying that in fact you can reduce any such definition that I started to formulate to a definition that is just a combination of very simple expressions like equations, negation of equations, so something that doesn't require quantifiers. And this is called quantify elimination. But in principle, in many examples, you see, it is when we use this criteria number 3, we could be satisfied with a little bit less than quantify elimination. You would be satisfied with some sensible way of classifying definable sets. And now we go to some classical examples. So this is a very old theorem of Tarsky. This is another beginning of the trend in model theory. Let's go there and look at structures one by one and apply those criteria. And so Tarsky, I think it is late 1940s, proved that if we take the field of complex numbers, or in fact any algebraically closed field of characteristic 0, so I use here characteristic 0 notation, assumption, but in fact the same true for any algebraically closed field of any characteristic. So in this very simple language where you only use addition, multiplication, you also have 0 and 1, and if you have 1, then you can build 2, 3, 4, and so on, and also rational numbers. So you can use all this as your named coefficients in your polynomials, and you can also say, of course, that there is a coefficient, an abstract coefficient, which can be any complex number, and so on. So if you work in this language with this structure, then the answer is very nice, that you have complete, explicit theory can be written down. It is quite obvious what you need to write down here. But it's not only complete, it is also categorical and has a quantify elimination, which in this case means exactly that it is just very simple formulas. And now the proof. The proof is actually rather straightforward, how we do it today. So, once you establish categoricity, you also establish completeness. And categoricity amounts to well-known Stein's theorem that says that any two algebraically closed fields of the same characteristic and with the same size transcendence base are isomorphic. So it is a basic fact of the theory of fields. Now, quantify elimination is just a little bit trickier. And in fact, it is the same argument, and it is in fact the again well-known to algebraic geometers, so-called Chevalier theorem, that you need just to understand what happens to the image of a constructible subset. So, what is constructible subset in the language of, I think that algebraic geometers use this language. So it is just Boolean combination of Zariski closed sets. So if you apply projection to Zariski closed, to a Boolean combination of Zariski closed sets, then you get again a Boolean combination of Zariski closed set. But if you do this in logic terms, what is projection? Projection is application of existential quantifier. So, so this is a classical trick of well, not trick. It is a classical way of eliminating quantifier, just to understand what happens to the projection. Now, of course, you have also this universal quantifier, the for all. But universal quantifier can be expressed in terms of existential quantifier and negation. So no problem here. Right. Next comes a bit trickier theorem. So it is referred to as Tarsus Zeitenberg. So if we look at the field of real numbers, it is almost the same statement, you can say. It is completed. So the axioms that we usually refer to as axioms of real closed fields, they're a bit trickier, and I'm not going to go there. So roughly, instead of saying that any equation with non-zero coefficients has a solution, you have to say that between two values with different sign of a polynomial. So if you have a polynomial with two different values, then between them there is a zero. And this theory does have elimination of quantifiers. So again, the in fact, it is very close analog to the statement that very close analog to Chevalier theorem, but now you have to express it in terms not of constructible sets, but in terms of semi-algebraic sets. And what is a semi-algebraic set? It is this very natural thing that I guess that many geometers are familiar with. So the notion of semi-algebraic. And it was Starsky who then went further and asked what happens with this structure. So suppose we have reals, and we are allowed to speak about reals in terms of in algebraic terms, in terms of addition, multiplication, inequality, and we have, for example, just one analytic function that's a classical one, exponentiation. And how about this? Can we, so is it tame, in fact? Well, Tarsky actually asked this in more specific logical terms this question. But the way that we understand it now, it is all about tameness. And so this brings us almost to modern times. Well, it was celebrated theorem of Alex Wilkie. It was a very difficult one. Actually, I guess it started the working on this problem was initiated, I guess, by Angus MacIntyre, then Lau van den Dries worked on this, and Alex was there from the very beginning. So and a lot of this work was just on a scrap paper. It took a long time to get to this result, and it's really interesting. And Alex explained this in his talk for Bourbaki seminar, that the actual breakthrough to this came after it was formulated, the condition of tameness, which since then we call O-Minimal. So O-Minimal is an abbreviation for order minimal. So all O-Minimal theories have this inequality sign in the language. Sorry, what is this? It is so this is really so the idea of OMinimality. It actually came with the so here is the definition of OMinimal in some very short form. So the idea is that in O-Minimal structures, you can classify very easily one-dimensional definable subsets. So there are no complicated one-dimensional definable subsets. Or to be very precise about this definition, that any definable subset on the real line is a union of finitely many intervals and points. But you see, this is a definition which was without the term O-Minimal, which was originally realized the usefulness of this by Lau van den Dries in 1986, I guess. And then Pillay and Steinhorn, they compared it with the developments with Morley theory of categoricity, which used the idea of one-dimensionality in terms of strong minimality. So they came up with the very abstract idea of what of this definition or minimal, where it is not necessarily the reals you should be we should be interested in, but any ordered structure. So we have a kind of linearly ordered set, and on this set some structure sits, and in terms of the structure, in terms of the language of the structure, you have that any definable subset of the line is a union of finitely many intervals and points. And they started to develop general theory in analogy with the theory of categoricity and stability. And it turned out to be very useful for eventually that Alex found a true technical proof of this. And so now we have many more O-minimal structures, and I'm sure that Bruno in his lectures will say much more about O-minimal structures and give more details. But so I will continue to talk about principles rather than these details. And here is another very important structure on the reals that has an analytic nature. So now what we have is so we pronounce it Rn, and so what we have the same field of reals, but now you have name, and so you can use this name to write formulas for any bounded analytic function. So it is supposed to be analytic on an open set which contains the cube. And so what we have, this is this theorem of van den Ries, where he already talked on this property of O-Minimality on the real line. So this theory has elimination of quantifiers and is O-minimal. But in fact, as van den Ries explains himself, so all that he needs to do is to understand and apply Gabriel's theorem that of 68, that image under projection of a bounded subanalytic set is bounded subanalytic. So again, it is analog of it is an analog of the Chevalier theorem. So we need to understand what happens with typical definable set. So typical definable set here is bounded subanalytic, and well, not exactly true that all are of this nature. So you have a combination of bounded subanalytic sets and unbounded algebraic sets, but this one is enough, and then it is a technical work of Lau van den Ries that makes it work. Okay, and now here is another thing that I noticed in some years later. So coming not from the reals, not from the interest in structures on the reals, but rather from the interest of the other side of model theory. It is stability theory and categoricity, and it is always the context of complex algebraic geometry, or in this case, it is context of complex analytic geometry. So the fact that I noticed it is that if we construct a structure, if we pick a structure, the universe of which is a compact complex manifold, or even a compact complex space, it would be the same argument, and considered it in the language which has names for analytic subsets on the Cartesian powers of this. then this structure has actually quantified elimination and is what technically we call omega stable, but even more, it is almost categorical. Well, almost categorical really means that you can decompose it into some sort of connected components which are categorical. It is a bit imprecise, but that's a good way of thinking about this. And I'm using this term on some of my next slides. And as you see in the slide, this theorem is actually, again, the proof of this theorem is similar to all the previous ones. All that you have to do here, it is not a difficult theorem at all. It is, but you have to notice this, that so in the world of analytic structures, there are some that are also very tame. Okay, it is a Graut-Remmert proper mapping theorem, and a little bit more. Okay, right. So here is also quite an important for in model theory and applications example, which we usually see as something that is between algebraic and analytic setting. So you really have a field, so formal structure, you have addition, multiplication, and you have a differential operator that satisfies this Leibniz rule. So in what you see in this slide, it is just one differential operator, but it is equally works with several differential operators, but you have to assume that they are commuting. They commute. So here you see the definition of differentially closed field. Well, under this definition, it is Abraham Robinson, long time ago in '59, proved that the theory of differentially closed fields of characteristic zero has a quantified elimination. So you can say that it is tame. It's interesting that at that time, so the whole idea of tameness was this completeness and quantified elimination. But it turned out later that people continued to prove some nice tameness property of the same structure. So it was later proved by Lenore Bloom that actually this object is also stable, and so it has a stable theory. So it is. It means that well, generally, yeah, I'm not going to give this precise definition of stability, but the idea here is that it is a kind of tameness that you see in absolute algebraic geometry. So algebraic geometry over algebraically closed field, like complex algebraic geometry. Unlike it is, unlike the case real algebraic geometry. So the difference is that in complex algebraic geometry, the properties are global, and in real algebraic geometry, it is it can be different. So definable set can be different, or set which is defined by an equation. Well, especially the equation that involve these analytic functions, can look drastically different in different locations. Okay, and so now I've come to formulating some general implications of this list of results. So most of them in the 1960s, 1970s. So this the proofs you might get an impression that it is just a reformulation of theorems like Groth-Remer theorem or Chevalier theorem, just this, but it is not. It is when you prove this theorem, you also systematically characterize all models, including what we call non-standard models of the same theory. So, for example, when you work with the reals or complex numbers, non-standard models they can contain the infinitesimals. So you do understand a lot of things about what happens in this extended world with infinitesimals. And so these non-standard models, you actually do construct through some kind of limit processes, a limit process, which technically is considering ultra product of existing models. You can start with one model and then consider ultra product of copies of this model. And so you have to deal, when characterizing those models, you have to deal with limits, and you do understand when proving this theorem. Without this, you cannot prove the theorem, that you do understand limits in families of definable subsets. And this implies uniformity statements. And here you see one of those uniformity statements, that if you have a family of, if you have a definable family of finite subsets, then necessarily there is an upper bound for the size of this subset. Now, if you work in a structure which has a well-defined notion of connected component, then similar is true also for the number of connected components. This is, for example, Hovansky theorem for exponentiation. And so these are the useful implications. But now I want to present here one of the earliest examples of applications. And this is application of Tarsky Zeitenberg theorem about reals, just the field of reals. So it is Lars Hermander. So you see the formulation. We look at the polynomial in n variables of the reals, and we look at a function that returns the minimum of the value of a polynomial when we fix the modulus of the argument. Yeah, so and also assumption is that our polynomial is such that it doesn't take negative values. And so if we assume that if we make this assumption that for any given positive real there is a bound such that over this bound we have the value of a polynomial bigger than this initial real, then actually we can determine very nice the limit form of this function, and this is quite important in this theory. Actually, I learned about this theorem when one of my colleagues, a professor in stochastic analysis at Oxford, approached me and asked to clarify this theorem. And so I went away, thought a little bit, and then realized how to prove it. And it is very direct consequence of Tarsky Zeitenberg. So the crucial point in all this is that this function, that fp of z, the function that is given to us in these terms, which do not that doesn't look very algebraic, these terms, because well, in fact, it is definable. See, well, we do define it in some informal way. Well, we have to use these words, which is not in our language. I mean, not in our formal language. We need to say it is minimum between this, that, such, and that have this property, and so on, satisfy this equation, modulus, and so on and so forth. But if you look at this is a very good exercise for beginners, students. We often give them this exercise, this sort of exercise. Well, but it would require to use quantifiers. You would have to say there is a value such that every other value is over this, and so on and so forth. So it is really an expression that is quite long and heavy with quantifiers in it. But it is definable. This is the main thing. And then the Tarsky theorem, Tarsky Zeitenberg says that it is equivalent to a very simple expression. And so this function is piecewise is given by algebraic functions. But more exactly, it is not just piecewise. You can use this uniformity that I mentioned to see that it has this form y is equal to coefficients times z to power a, where a is some rational number plus lower terms, and that's it. So this is a beautiful application, and so this is a beautiful application of one of the basic theorems of very simple things. So we shouldn't be surprised very much that when you prove similar theorems for things that involve exponentiation, then that's much more powerful, has a potential much bigger. Okay, so from all this experience, we arrive at following classification principles. So so we can classify, in fact, the structures. We now look at structures as being part of some classification matrix where we have dividing lines like categoricity and these levels of stability or minimality. There are other forms of this. then the bridges between these different levels are this dimension theory, dependence, geometric stability theory, the theory of groups in these structures, and so on. And among examples, there are literally dozens and hundreds of examples from algebraic geometry, complex and real geometry, periodic analysis, algebra, differential algebra, Diophantine geometry, dynamical systems. And yeah, I like this thought that in fact the way that we model theorists now think about this classification theory, it is like for mathematics is as illuminating. It has a potential to be as illuminating as Mendeleev periodic table for chemistry. And let me show you on the internet there is a site. This is a site where designed by some of my colleagues. So you have this map of the universe of. So you have you know that's the way we are thinking about the universe is populated by various mathematical structures, and you see here. So here we come into the world of O-minimal structures, and if we press this one, oh, sorry, yeah, I pressed the wrong one. So here you see on the right lower corner, you see that we have this real closed field that we just talked about as one example. Then we also have the field with exponentiation, and then there are some other examples. Now, if we go into this corner, that we see a lot of other structures with other examples. So here are what we call strong minimal structures. So algebraically closed fields and vector spaces and so on. And then so we have, as you see on the left, we have O-minimal, we have strongly minimal. So here we have so-called DP minimal and various kinds of this, and then we have various kinds of stable structures and super stable structures. So again, if you look at this DP minimal, what you see in the right lower corner, so there is this very important example. So the abbreviation for it is ACVF. It is algebraically closed valued fields, and Hrushevsky used it in very effective way in proving. So it's a lot of work around it, and Hrushevsky and Lazaire proved some great results in non-Archimedean analysis, Berkovich spaces, and answering some open questions. So it is so a lot of applications that sit here on this picture, and so that's unfortunately it is not complete. So in fact, there must be hundreds of such objects that marked by points here, and so it is of good use to specialists this, but to make use of it for broader mathematical community, of course, we should put in much more of known examples, known and useful examples. Okay, that's it. That's what I plan to present for today.
Thank you very much. So I think everybody should feel free to unmute yourself or turn on your video if you want. So let's thank Boris for a really illuminating talk.
Thank you.
Thank you.
Thank you.
Thank you.
So now, I think we have plenty of time for some questions. So does anybody have any questions? Maybe let me ask a question. What about other types of structures that are like maybe less related to complex geometry?
What do you mean, other what?
Well, maybe are there similar types of things that are happening, but without the real numbers, for example? In some other
Yes, sure. Yeah, well, it is, as I said, you see, it's, so you have these different boxes in this classification theory. And so it is different degrees of tameness in these boxes. So depending, of course, on so for example, in non-Archimedean analysis, you would have the p-adics and so geometry over p-adics, or geometry over this so-called CP, the completion of the algebraic closure of the completion of p-adics, or the other way around. And by the way, this is the application that I just mentioned about Hrushevsky and Lazare. But in principle, yeah, I'm going to talk tomorrow about some other ways of thinking about the structures that lead into the problems in arithmetic, in transcendental functions, and other such things. Yes, but I would repeat again that this approach and this classification principles, they are extremely broad, and by the way, this is I didn't mention this, but it is all due. I mean, the main scheme of this classification principles is due to Saharon Shelach. It is absolutely great achievement that he drew the main lines of this classification principles, and he never thought about anything applications, never thought about geometry, and this is all you know, it comes from certain combinatorial thinking, and then suddenly you find yourself deeply involved in geometry.
Okay. So does anybody have any further questions? Okay, so let's thank Boris again for a nice talk.
Thank you.